Imagine that every map you have ever seen is quietly lying to you. Not because the stars are in the wrong places, not because the galaxies are drawn too close together, but because every map makes the universe feel like an object sitting inside a larger emptiness, a bubble in darkness, a sphere growing into a room, a cosmic explosion spreading outward into space that was already waiting for it. And once that picture enters your mind, one question becomes almost impossible to avoid. If the universe is expanding, what is it expanding into? It sounds simple, but it cuts straight into the deepest problem in cosmology, because every expanding thing we know needs room around it. Smoke expands into air. Water spreads across a floor. A balloon swells into the space of the room. So when we hear that the universe is expanding, we imagine an edge moving outward. But the universe may not have an edge. It may not have a center, and it may not be moving into anything at all. Before we begin, if you enjoy calm journeys through space, time, and the stranger parts of reality, subscribe to the channel, leave a like, and write a comment telling us where you are watching from and what time it is for you right now. Somewhere, another person may be hearing this under a morning sky, while someone else is listening in the middle of the night. Tonight, you are watching the Space for Sleep channel, talking about one of the strangest questions in the study of the cosmos. The universe is expanding, but into what? The first thing we have to do is slow the question down. When someone says the universe is expanding, it sounds as if the universe is a thing, like a cloud or a fireball, getting larger inside a place around it. That is the picture most people naturally build. It feels obvious because our entire life is spent inside containers. A cup contains water, a room contains furniture, a city contains streets, a planet contains oceans and mountains. Even the sky above us feels like a dome, even though we know it is not. So when we hear the word expanding, our brain reaches for the same kind of image. There is the universe, and then there is the outside. The universe grows, and the outside gives it space to grow into. But cosmology asks for a different kind of thinking. On the largest scales, galaxies are not flying through a fixed cosmic room like sparks from a fire. Instead, the distances between very distant galaxies increase because space itself is changing. The stage is not still while the actors move across it. The stage itself stretches, and the actors are carried farther apart by that stretching. That sentence sounds simple, but it is one of the most difficult ideas to actually feel. If you place two dots on a rubber sheet and stretch the sheet, the dots become farther apart, even if the dots are not crawling across the rubber. If you bake raisin bread, the raisins separate as the dough rises, even though each raisin can remain almost still inside its own small piece of dough. If you draw galaxies on the surface of a balloon and inflate it, every drawn galaxy sees the others moving away. These analogies are useful, but they are also dangerous because each one secretly smuggles in and outside. The rubber sheet stretches inside the room. The bread expands inside the oven. The balloon inflates into the air around it. Your mind sees the example and immediately asks the same question again. What is outside the universe, the way the room is outside the rubber sheet? That is where the analogy breaks. The rubber sheet and the balloon are objects inside our space. The universe, in cosmology, is not supposed to be an object inside ordinary space. It includes ordinary space. It includes the distances. It includes the measuring rods. It includes the idea of direction between places. When space itself expands, there may be no surrounding empty room required. This is not just a philosophical trick. It comes from evidence. The evidence arrived through light. In the early 20th century, astronomers looked at faint spiral smudges in the night sky and began to realize they were not small clouds inside the Milky Way. They were other galaxies, enormous islands of stars far beyond our own. Their light had crossed distances so large that the numbers barely behaved like normal numbers anymore. When that light was split into its colors, something strange appeared. The fingerprints of atoms in those galaxies were shifted. Hydrogen still looked like hydrogen. Calcium still looked like calcium. The same patterns were present, but the patterns had moved toward longer, redder wavelengths. The farther away many galaxies were, the more their light appeared stretched. This is cosmological redshift. It is not simply that light is tired. It is not just that galaxies are moving through space the way a car moves down a road. On the largest cosmic scales, the wavelength of the light is stretched as space expands during the light's journey. A photon can begin as visible light in a distant galaxy, travel for billions of years, and arrive at our telescopes as infrared light, because the universe expanded while that photon was in flight. In that one fact, the universe reveals something extraordinary. Space is not a passive emptiness. It has history. A beam of light does not merely cross the universe. It carries a record of how the universe changed while the beam was traveling. This is why distant galaxies are not just far away. They are old views of the universe. Looking across space is also looking backward in time. A galaxy whose light has traveled for 10 billion years is not seen as it is today. It is seen as it was when the light began its journey, when the universe was younger, denser, and different from the universe around us now. The night sky is not a single moment. It is a layered archive. Nearby stars show us recent history. Distant galaxies show us ancient history. The faintest deep fields show us galaxies from a time when the cosmos was still young, when the first large structures were still assembling from the dark. And across that archive, the same pattern appears. Distant galaxies are, on average, receding from us. More precisely, the space between us and them is growing, and the farther away they are, the faster that distance increases. This relationship is now known through the Hubble-Lemaitre law. It tells us that recession speed increases with distance, not because Earth is at the center of an explosion, but because a uniform expansion makes every distant observer see a similar pattern. If every galaxy sees the others moving away, then no galaxy has to be the center. Imagine standing on one raisin in rising dough. Every other raisin seems to drift away from you. But if you could stand on any other raisin, the same thing would happen there. Each raisin would appear to be surrounded by an expanding universe of other raisins. None of them has to be the special center of the bread. The same idea works in space. From the Milky Way, distant galaxies appear to recede. From a galaxy billions of light years away, the Milky Way would appear to recede. From another galaxy in a different direction, the same general pattern would appear again. Cosmic expansion does not point to us as special. It removes the need for a special point. There is no central galaxy from which everything fled. There is no known location in space where the Big Bang happened while other places waited outside it. The Big Bang happened everywhere. Because it was not an explosion inside space, it was the early, hot, dense state of space itself. That sentence is easy to say and hard to hold in the mind. When we hear Big Bang, we imagine a blast. We imagine a black emptiness, then a tiny bright point, then an explosion throwing galaxies outward. It is dramatic. It is visual. It looks good in a film. But as a picture of modern cosmology, it is deeply misleading. The Big Bang was not matter exploding into a pre-existing void. It was a time when the universe was much hotter, much denser, and much smaller in the sense that distances between things were compressed. Everywhere that is now spread across the observable universe was once much closer together, not closer to one location, closer everywhere. There was no empty stage waiting for the universe to enter. The stage itself was in the early state. If you rewind the expansion of space, distant galaxies do not fly back toward Earth specifically. All large distances shrink. Galaxy clusters become closer to other clusters. Matter becomes hotter. Radiation becomes more energetic. the universe becomes denser in every direction. The story does not converge on a point in space like a bomb fragment map. It converges on an earlier condition of the whole cosmos. This is why the question, "What did the universe expand into?" may be asking for the wrong kind of answer. It assumes the universe is surrounded by space. But space is part of the universe. To see how strange this is, imagine asking what is north of the North Pole. The words are understandable, the sentence has grammar. But on the surface of Earth, north is a direction that stops making sense at the pole. You can move away from the pole in many directions, but none of those directions is farther north. The question does not fail because you are not clever enough. It fails because the concept reaches a boundary where it no longer applies. The same may be true for asking what the universe expands into. The word "into" belongs to ordinary objects inside space. It may not apply to space as a whole. It shows that our imagination evolved for rooms, roads, horizons, containers, and objects. We are very good at understanding things that sit inside other things. We are less prepared for a reality where the thing changing is the meaning of distance itself. For most of human history, space looked like emptiness. It was the blank arena between objects. Stars were objects. Planets were objects. People were objects. Space was the nothing between them. Modern physics changed that. In Einstein's general relativity, space and time are not a silent background. They form a dynamic geometry. Matter and energy influence that geometry, and the geometry influences the motion of matter and light. Gravity is not only a force pulling objects through space, it is also the curvature of space-time telling objects how to move. Once space-time can curve, stretch, and evolve, the universe becomes far stranger than a room full of galaxies. A room has walls, a floor, a ceiling, a background outside the things in it. Space-time does not need to be a room in that sense. It can have its own internal geometry. It can be finite or infinite. It can be flat on large scales or curved in ways difficult to visualize. It can expand not by moving into another space, but by increasing the distances measured within itself. This is where the balloon analogy becomes useful again, if we use it carefully. Imagine creatures living on the two-dimensional surface of a balloon. They cannot move into the air outside the balloon. Their entire universe is the surface. They can go forward, backward, left and right along that surface, but they have no direct experience of up and away from the surface. As the balloon inflates, every point on the surface becomes farther from every other point measured along the surface. The creatures see distances increase. They observe galaxies drawn on their surface moving apart. They conclude their universe is expanding. If one of them asks, "What is our universe expanding into?" we, as three-dimensional observers, can say, "It is expanding into the surrounding air." But that answer uses a dimension the surface creatures do not need in order to describe their own expanding world. Their mathematics can describe the expansion entirely from within the surface. They can measure distances, angles, curvature, and change without ever pointing to the outside air. For our universe, the situation may be similar, but we must be careful. We are not saying the universe is literally the surface of a balloon. We are not saying there is definitely a higher dimensional room around it. The analogy only shows that expansion can be understood internally. A space can grow in its own measured distances without requiring every observer inside it to identify a surrounding container. The outside may be unnecessary, it may also be meaningless. Or it may exist in some deeper theory we do not yet understand. Cosmology has to hold all of these possibilities without pretending we know more than we do. What we can say is this: the expansion we observe does not require a visible edge moving outward. It does not require a central point. It does not require galaxies flying away from Earth through static emptiness. The data are explained by a universe whose large-scale distances grow with time. But it becomes more unsettling when we look at the beginning. The early universe was not filled with galaxies. It was not a dark field with stars sprinkled through it. It was hot, dense, and bright in a way that no ordinary place today can reproduce on cosmic scales. For the first hundreds of thousands of years, the universe was filled with a plasma of charged particles and radiation. Light could not travel freely for long distances because photons kept scattering from free electrons. The universe was not transparent. It was more like a glowing fog, where light existed everywhere, but could not stream cleanly across space. Then the universe expanded and cooled. Protons and electrons were finally able to combine into neutral hydrogen atoms. With fewer free electrons in the way, light could travel. The fog lifted. The universe became transparent. That first, freely traveling light is still around us today. It has been stretched by cosmic expansion for more than 13 billion years. What began as hot visible or infrared radiation has cooled into microwaves. We detect it as the cosmic microwave background, a faint afterglow coming from every direction in the sky. This glow is not coming from an edge of the universe. It is not a wall around creation. It is the oldest light we can see, released when the observable universe became transparent. It surrounds us because every direction we look eventually reaches a region whose light has taken nearly the age of the universe to arrive. The cosmic microwave background is often called a baby picture of the universe, but even that phrase can mislead us because it sounds like a photograph taken from outside. It is not a picture of the universe as a ball. It is a map of ancient light arriving from all directions. It shows tiny temperature differences, small density seeds, and the early pattern from which galaxies and clusters would eventually grow. It is a fossil record of a time before stars, before planets, before the Milky Way, before any eye could look upward and ask what space was. And it tells us something profound. The universe was once very different. Not just the objects inside it. The entire condition of space, matter, and radiation was different. The expansion is not a minor detail. It is the spine of cosmic history. As space expanded, radiation cooled. As radiation cooled, atoms formed. As atoms formed, gravity could slowly gather matter into clouds. Those clouds became the first stars. Stars forged heavier elements. Galaxies assembled. Planets formed from enriched debris. Eventually, on one planet around one ordinary star, atoms arranged themselves into beings capable of reconstructing this whole history from faint light in the sky. The story of expansion is the story of why anything looks the way it does now. Without expansion, the early universe would not have cooled in the same way. Without cooling, stable atoms would not have formed when they did. Without atoms, no stars as we know them. Without stars, no carbon, oxygen, iron, or planets. Without planets, no oceans, no rocks, no air, no life listening to a video about the universe in the dark. So the question is not just where the universe is going. The question is why reality has a history at all. When we say space expands, we are also saying the universe has a before and after built into its large-scale structure. A photon from the early universe does not merely arrive late. It arrives changed. A galaxy at extreme distance does not merely look smaller. It appears from an earlier cosmic chapter. The farther we look, the deeper into the past we see, until eventually we reach the glowing fog beyond which ordinary light cannot show us anything directly. This creates a boundary around our knowledge, not a physical wall, a horizon. The observable universe is the region from which light has had time to reach us since the beginning of the hot Big Bang phase. It is not the entire universe, unless the entire universe happens to be no larger than what we can observe. Most cosmologists suspect the whole universe is much larger than the observable part, perhaps enormously larger, perhaps infinite. This distinction matters more than almost any other. When people imagine the universe expanding, they often imagine the observable universe as the whole thing, a sphere with us near the center, surrounded by a boundary, growing into darkness. But the observable universe is centered on every observer. You have an observable universe centered on Earth because light has only had a limited amount of time to travel to us. A civilization in a galaxy 10 billion light-years away would have its own observable universe, centered on itself, overlapping with ours in some regions and reaching into regions we cannot see. The edge of our observable universe is not the edge of all existence. It is the edge of our view. This is like standing in a foggy field at night with a lantern. You can see only so far. The boundary of your vision moves with you. It tells you something about your situation, not necessarily where the field ends. The universe is more complicated than fog, because the limitation comes from time, light speed, and expansion. But the lesson is similar. A horizon is not always a wall. On Earth, the horizon is the line beyond which the planet curves away from your view. You can travel toward it, but you never arrive at a final painted line on the ground. The horizon shifts as you move. It is real as a limit to what you can see from one position, but it is not an object you can touch. The cosmic horizon works in a deeper way. There are regions so far away that their light has not reached us yet. There may also be regions whose light will never reach us, because expansion carries them away so quickly that signals emitted now can never cross the growing distance. The future universe may become lonelier, not because galaxies vanish locally, but because more and more of the distant cosmos slips beyond our reachable view. This is where expansion becomes quietly terrifying. It does not tear apart atoms or solar systems today. It does not make your room grow in any meaningful way, because local forces hold small structures together. Gravity holds galaxies and clusters. Electromagnetism holds objects. Chemical bonds hold your body. Cosmic expansion dominates only on the largest scales, where galaxies are not bound strongly enough to resist the stretching of space between them. But on those largest scales, expansion changes what the universe can ever reveal. There are galaxies whose light we see now as they were billions of years ago, but whose present state is already beyond any message we could receive. We see their ancient ghosts, not their current lives. The telescope does not show us the universe as it is everywhere right now. It shows us a carefully delayed collection of arrivals. The deeper the view, the older the message. This is why the idea of a cosmic edge is so seductive and so dangerous. Our best images of the early universe look like a sphere around us, because we receive ancient light from every direction. But that sphere is not a shell at the edge of space. It is a shell in time. It marks the distance from which light, released when the universe became transparent, is reaching us now. If you could magically travel to one of those regions, you would not find a glowing wall. You would find galaxies, darkness, stars, and local history, assuming such structures formed there. And from there, if you looked back toward our region, you would see our ancient light in your own sky. Every observer is surrounded by their own past. So when we ask what the universe expands into, we may be confusing the edge of our sight with the edge of reality. Still, the question remains powerful. Even if there is no edge to the observable universe, could the whole universe have an edge somewhere beyond what we see? The honest answer is that we do not know. The observable universe appears on large scales remarkably uniform. In every direction, the cosmic microwave background is almost the same temperature, with tiny variations. Galaxies form a cosmic web, but averaged over enormous distances, the universe looks similar in different directions. This supports the idea that our region is not a special central place. Measurements also suggest that space is very close to flat on large scales. In geometry, flat does not mean two-dimensional, and it does not mean empty. It means that the rules of large-scale geometry are close to the familiar rules of Euclidean space. Parallel lines remain parallel. Triangles have angles that add to about 180 degrees. And space does not show strong overall curvature within what we can observe. A flat universe could be infinite. If the whole universe is infinite, then expansion does not mean it grows from finite to larger finite. Infinite space can still expand because distances between points increase. Infinity does not need to become a bigger infinity in the ordinary sense. The scale factor changes. The measured separation between unbound galaxies grows. Every large region becomes more spread out, even if there is no total edge and no outside boundary. This is another place where intuition breaks. How can something infinite expand? Because expansion is not necessarily about adding new border space at an edge. It is about changing the distance scale everywhere. Take an infinite number line. Mark points at every whole number. Now imagine stretching the scale so that each neighboring mark becomes 2 units apart instead of 1. The line was infinite before. It is infinite after. Yet the distances between marked points have increased. No edge moved. No outside was required. The same kind of thinking can apply to an infinite universe. It can be infinite at every moment while still having a changing scale. The expansion is not the universe needing more room. It is the universe's own metric changing with time. Metric is a technical word, but the idea is simple. A metric tells you how distances are measured. In ordinary life, we assume the ruler is stable. 1 meter today is 1 meter tomorrow. But in cosmology, the distance between faraway, unbound galaxies can increase because the scale of space evolves. The galaxies may sit at nearly fixed coordinates in the expanding cosmic grid, while the physical distance corresponding to those coordinates grows. These coordinates are not like street addresses in a city. They are part of a mathematical description of the expanding universe. But they help avoid the false picture of galaxies flying through static space like debris. The debris picture is not completely useless. Galaxies do have their own motions. The Milky Way and Andromeda are moving toward each other because they are gravitationally bound. Stars orbit within galaxies. Galaxy clusters have internal motion. Space is not a perfectly smooth grid with frozen dots. But on the largest scales, after averaging over local motions, the expansion pattern appears. The cosmic web stretches, voids grow larger, distant clusters drift beyond each other's future reach. And because space expands everywhere, there is no unique center to point back toward. This brings us back to the Big Bang, because the word bang still creates the wrong mental image. Imagine an explosion in a warehouse. There is a center where the explosion begins. There are walls that may be damaged. There is air into which smoke expands. If you record the debris and rewind the motion, fragments converge on one location. The explosion has a place. Now compare that with cosmic expansion. If all distant galaxies are receding from all other distant galaxies, rewinding does not identify one central warehouse. It makes the whole distance scale smaller. Every region was once hotter and denser. Every region shares the early state. The Big Bang is not a point over there. It is a time in the past of everywhere we can observe. You are not far from where the Big Bang happened. You are inside what the Big Bang became. Every atom in your body exists in the later, cooled, structured universe that grew from that early condition. The place where you sit, the air around you, the planet under you, and the deep sky above you all trace back to the same compressed, hot beginning of the observable universe. That does not mean our local matter was always assembled as Earth, or as the Milky Way, or even as atoms. It means the space and energy that would eventually become our region were part of the early universe too. There is no direction you can point and say, the beginning was that way. The beginning is behind every direction in time. This is why cosmology often feels like it is turning the mind inside out. We are used to locating things in space. Where is the mountain? Where is the moon? Where is the nearest star? But the Big Bang is not located in space the way a mountain is. It is located in the past. When you ask where it happened, the best answer is here, there, and everywhere, when the universe was young. That still leaves a deeper mystery. If space itself can expand, what determines the expansion? In general relativity, the contents of the universe influence its evolution. Matter, radiation, curvature, and dark energy all affect how the scale factor changes over time. The universe does not expand at a constant, simple speed like a balloon being inflated by a steady pump. Its expansion history has phases. In the early universe, radiation was more important. Later, matter played a larger role. Gravity slowed the expansion compared with what it would have done otherwise. Then, billions of years later, observations of distant supernovae revealed something unexpected. The expansion was not merely continuing, it was accelerating. The universe is expanding faster in a particular sense over time. Not because galaxies are firing engines, not because they are choosing to flee. The expansion rate of space is being influenced by something we call dark energy, a name that sounds more like science fiction than science, but simply marks our ignorance. Dark energy is the label for whatever causes the observed accelerated expansion. We do not know its true nature. It may be related to the energy of empty space, something like Einstein's cosmological constant. It may be a field that changes over time. It may point to a deeper modification of gravity on cosmic scales. It may be something our current language is not yet built to handle. But its effect is seen in the history of the expanding universe. And this effect sharpens the question of what the universe is expanding into. Because if the expansion is accelerating, it becomes tempting to imagine an outward push from outside, something beyond the universe pulling it open, some larger emptiness drawing space into itself. But that is not what the evidence requires. Dark energy, as used in standard cosmology, is not a wind from beyond the edge. It is not pressure from an outside room. It is part of the universe's own description, affecting the expansion of space from within the equations. The universe does not need an external atmosphere to expand. It may be more like a rule changing everywhere at once. This is difficult, because the word everywhere already assumes space. When cosmologists say expansion happens everywhere, they do not mean every object grows. They mean that, on average, and at enormous scales, the distance between unbound regions increases. There is no surface where new space is being manufactured like foam at an edge. The change is distributed through the geometry. Think again of the balloon surface, but remove the outside from your attention. For the two-dimensional creatures, the expansion is not happening at a rim. There is no rim. Every distance on the surface grows. A galaxy 1 million surface units away becomes 2 million surface units away after enough expansion. Another galaxy in another direction does the same. There is no border where the action occurs. In our universe, if it is infinite, there is no rim at all. If it is finite but unbounded, it could have a total volume without an edge, the way the surface of Earth has a finite area, but no edge you can fall off. That is not saying space is exactly like Earth's surface. It is only a way to understand how finite does not always mean bordered. A finite, unbounded universe could expand by increasing all internal distances while still lacking an edge. An infinite universe could expand by increasing its scale while remaining infinite. A universe with more complicated topology could connect to itself in ways that make long journeys theoretically return you to where you started, although no evidence currently shows such a wraparound within the observable region. Different possibilities remain open because we see only a limited portion of the whole. That limitation is not a failure of telescopes alone. It is built into cosmic time. Even a perfect telescope cannot see light that has not arrived. It cannot see beyond the opaque early plasma using ordinary light. It cannot receive signals from regions forever carried beyond our horizon. So, the universe gives us evidence, but not unlimited evidence. We are like deep-sea explorers trying to infer the shape of the entire ocean from the pressure, temperature, currents, and life in a vast but still limited region. The data are real. The reasoning can be powerful. But there may always be a difference between the observable universe and the whole universe. This is why careful language matters. The observable universe is about what can be seen from here. In principle, given the age of the universe and the speed of light. The whole universe is everything that exists in the cosmic space-time, whether or not its light can ever reach us. The difference between these two ideas is the difference between a horizon and a border. A horizon depends on the observer. A border would belong to the universe itself. We have strong evidence for horizons. We do not have evidence for a physical border. There may be no last galaxy in the whole universe. There may be galaxies beyond the part we can see, perhaps endlessly many. There may be regions where the same laws hold, the same cosmic web continues, and observers there ask the same question while looking back toward a horizon that includes us only as an unreachable part of their ancient sky. An infinite universe does not have a center because every point can be treated as a center of its own observable region. It does not have an edge because no matter how far you travel, there is more space. It can still expand because expansion changes distances, not because a boundary advances into a container. If this is true, then the answer to what is the universe expanding into is, it is not expanding into anything. It is expanding in the sense that its own internal distances are increasing. But that answer can feel unsatisfying. It feels like being told that the question is wrong when the question feels obviously right. And maybe that discomfort is not a weakness. Maybe it is the point where human-scale imagination meets cosmic-scale reality. Our intuition evolved inside a tiny gravity-bound environment. We learned to understand thrown stones, flowing water, shelters, caves, trees, rivers, animals, tools, and fire. Everything around us was surrounded by something else. Every movement happened through a place. Every expansion needed room. Then we built mathematics and telescopes, and those tools carried us into a realm where the basic assumptions of daily life fail. At high speeds, time changes. Near massive objects, space curves. At quantum scales, particles do not behave like tiny balls. At cosmic scales, distance itself can evolve. The universe is not obligated to match the picture-making habits of a primate brain on a small planet. Still, we need pictures. Without pictures, the idea becomes too abstract to hold. So we use balloons, dough, rubber sheets, grids, and horizons. Then we remind ourselves where those pictures fail. We climb the ladder, then we do not mistake the ladder for the destination. The universe is not expanding from a center into a surrounding emptiness. The measurable distances between faraway, unbound regions of the universe are increasing with time. This expansion is part of the geometry of space itself. The question of what lies outside may not be required by the physics we observe. That is the stable ground. From there, we can ask the more dangerous questions carefully. If the universe does not expand into anything, does that mean there is nothing outside it? Not exactly. It means our current description does not need an outside. It may not define one. In general relativity, the universe can be modeled as all of space-time, not as an object placed inside a higher room. Asking what is outside space-time may be like asking what time it was before time began, or what is north of the North Pole. The words are familiar, but the concepts may no longer connect to anything physical. However, physics is not finished. There are speculative ideas in which our universe could be part of a larger structure. Some versions of inflation suggest regions beyond our observable universe may have different histories. Some ideas in theoretical physics discuss higher dimensions, branes, or a multiverse. Quantum gravity may eventually change how we understand the beginning, time, and the global structure of reality. But these ideas are not the same as the simple image of the universe expanding into empty black space. They are deeper and more uncertain. If there is a larger reality, it may not be space in the ordinary sense. It may not have directions like left-right, up and out. It may not be something a spaceship could enter by reaching the edge of the universe, because there may be no edge to reach. It may be mathematical, dimensional, quantum, or completely beyond the categories we use for everyday places. This is why the title question is so powerful. The universe is expanding, but into what? It begins as a request for a location. It becomes a test of whether location itself is fundamental. To see this even more clearly, think about the difference between moving through space and being carried by expanding space. If a spaceship leaves Earth, it travels through local space. It has a speed relative to nearby objects. It burns fuel. It follows a path. It cannot locally outrun light, because the speed of light is the cosmic speed limit for motion through space. But distant galaxies can recede from us faster than light, because this is not local motion through space in the same way. It is the growth of distance due to expanding space over enormous scales. No galaxy locally breaks the speed of light in its own neighborhood. The separation between us and that galaxy can still increase faster than light because the space between is expanding. This is not a loophole for faster-than-light travel. It is a sign that cosmic distances are not like distances on a static map. The map itself changes while the journey is being drawn. When people first hear this, it can sound impossible. If something is moving away faster than light, how can we see it? The answer depends on timing, expansion history, and the path light takes through changing space. Some photons emitted long ago by galaxies now receding faster than light can still reach us because the expansion rate changed over time and because the photon made progress through earlier conditions. Other photons emitted now from sufficiently distant regions may never arrive. The universe is not merely large, it is dynamically large. Its size is not just a number, it is a relationship between distance, time, expansion rate, and light. This is why the observable universe is much larger in radius than the simple age of the universe times the speed of light might suggest. The universe is about 13.8 billion years old, but the most distant regions we can observe today are much farther than 13.8 billion light-years away in present distance terms, because space expanded while the light was traveling. The light took about 13.8 billion years to arrive, but the place that emitted it is now far more distant than 13.8 billion light-years. Again, the map changed during the journey. This one idea explains why cosmology is so different from ordinary astronomy. Ordinary astronomy can often treat space as a stage. A planet orbits a star. A comet passes near the sun. A spacecraft travels from Earth to Mars. These are difficult problems, but the background space does not usually change enough to matter. Cosmology cannot do that. When the light travel time is billions of years, the expansion of space becomes part of the observation. You cannot separate the object from the history of the universe between you and the object. Every deep image is also a measurement of expansion. In the far future, if dark energy continues to dominate, distant galaxies beyond our local gravitational group may disappear from view. Their light will become more redshifted, more diluted, and eventually unreachable. Future astronomers in the merged Milky Way and Andromeda might look out and see a much emptier universe. Without records from the past, they might not easily discover cosmic expansion at all. The evidence we have now exists because we live at a particular cosmic time, late enough for galaxies, planets, and observers, early enough for the distant universe to still be visible. That is a strange thought. The universe is old enough to tell us its story, but not so old that the story has faded completely beyond the horizon. When you look at deep space, you are seeing evidence that future observers may lose. Expansion is not only a process in the background. It is an eraser, moving slowly across cosmic knowledge. But before we go too far into the future, we need to return to the original question and examine the word into. Into implies a destination or container. It implies that expansion happens across a boundary from occupied space into unoccupied space. It works perfectly for gas expanding into a vacuum chamber. It works for a crowd spreading into an empty stadium. It works for the ripples of an explosion moving through air. But the universe is not known to have a boundary between occupied and unoccupied external space. In standard cosmology, expansion is described by the scale factor, a function of time that tells us how distances between co-moving points change. Co-moving points are points that move with the general expansion, ignoring local motions. If the scale factor doubles, the distance between two faraway unbound galaxies doubles, assuming they remain co-moving. No outside direction appears in that description. The equations do not ask which way the universe expands. They ask how the internal scale changes with time. This difference is subtle but enormous. A firework expands outward from a center. You can stand outside the firework and watch fragments move through space. The universe expands in a way where every sufficiently distant observer can consider themselves at rest with respect to the cosmic expansion and see other distant regions receding. There is no outside vantage point included in the model. There is no privileged place from which the whole thing is watched. We are inside the phenomenon we are trying to describe. That may be the most important emotional fact in cosmology. We do not look at the universe from outside. We look from one small region within it. Every telescope, every detector, every equation, every map is created by beings embedded in the same expanding space-time they are studying. We are not observers standing in a museum looking at a sculpture called the universe. We are patterns inside the sculpture, trying to infer its shape from echoes moving through it. And because we are inside, our language keeps trying to escape to an outside viewpoint we may not have. What is it expanding into? Where is the edge? What was before the beginning? What is outside everything? These questions may be meaningful in a future theory. But in the theory that currently describes cosmic expansion, they are not always well defined. The universe can have a beginning in time without a border in space. It can have a finite observable region without a physical edge. It can expand without moving into a container. It can be everywhere and still change. None of this removes the mystery. It makes the mystery sharper. Because if there is no outside needed, then expansion is not a drama happening at the edge of the universe. It is happening in the silent distance between the larger structures. It is happening in the relationship between galaxy clusters separated by cosmic voids. It is happening in the wavelength of ancient light as it travels. It is happening in the future visibility of everything beyond our local gravitational island. The universe is not expanding somewhere far away. The expansion is woven into the way far away is defined. That is why the night sky can look still while the cosmos changes. The stars you see with your eyes are mostly nearby stars inside the Milky Way. They are gravitationally bound to our galaxy. Their positions shift slowly because of local motions, not because cosmic expansion is pulling them away from us. The constellations do not visibly swell with the expansion of the universe. Even the Milky Way itself is not expanding in the ordinary cosmological sense. Gravity holds it together. The solar system is not expanding. Earth is not expanding. Your body is not expanding because the universe expands. This is another common misunderstanding. Expansion is not a force stretching everything equally at every scale. It is a large-scale behavior of space-time that becomes significant, where gravitational binding is weak enough and distances are enormous enough. Inside galaxies, local gravity wins. Inside atoms, electromagnetic forces win. Inside everyday objects, chemical bonds and material structure win. The universe expands between galaxy clusters across the vast underdense spaces where structures are not bound together. So if you imagine every ruler on Earth slowly growing, that is not right. If the ruler grew with the space around it, you would not measure expansion. In reality, local rulers remain held together while the distances to remote, unbound galaxies change. This is why redshift is so important. It gives a way to detect expansion across cosmic distances, not by watching galaxies visibly move across the sky, but by reading the stretched light they send. Light becomes the messenger, and the message is written in wavelength. A photon traveling through expanding space becomes a kind of clock without hands. Its stretch tells us that the universe changed during the journey. The more the universe expanded while the photon traveled, the greater the redshift we measure. For nearby objects, redshift can be complicated by local motion. A galaxy moving toward us can have blue shift. Andromeda, for example, is moving toward the Milky Way because our galaxies are gravitationally bound within the local group. But for very distant galaxies, the overall expansion dominates, and redshift becomes a key sign of cosmic scale. This is how the universe teaches us its motion without needing an edge. Not by showing a border, by stretching light. Not by revealing a center, by making every distant view participate in the same pattern. Not by letting us stand outside, by forcing us to read the inside carefully. Now consider what would happen if the expansion were reversed in the equations. As we look backward in time, the scale factor shrinks. Galaxies were closer. Matter was denser. Radiation was hotter. The cosmic microwave background was once not microwave at all, but much higher energy radiation. Earlier still, atoms could not exist. Earlier than that, nuclei were forming. Still earlier, particles and fields existed in states far beyond ordinary experience. The deeper we go, the less the universe resembles a place filled with objects, and the more it resembles a condition described by temperature, density, expansion rate, and quantum fields. At some point, our current theories lose certainty. General relativity and quantum mechanics both work extremely well in their domains. But the earliest moments of the universe require conditions where gravity and quantum physics must both be treated together. We do not yet have a complete tested theory of quantum gravity. So when people speak confidently about the exact first instant, we should be careful. The Big Bang model is strongly supported as a description of the hot, dense, expanding early universe. It does not automatically answer every question about an absolute beginning. It does not tell us, with final certainty, whether time itself began there, whether there was a prior phase, whether inflation occurred in a larger setting, or whether the word before has any meaning at the deepest level. This matters because the question, what is the universe expanding into, is often tied to another question. What came before the universe? Both questions push our concepts to their limits. If time is part of the universe, then asking what happened before time may be like asking for a place outside space. The sentence is easy to form, but the reality it points to may not be defined. Yet, if a deeper theory shows that our hot Big Bang phase emerged from something prior, then before may regain a new meaning in that theory. The difficulty is not that scientists refuse to ask. The difficulty is that good answers require equations and evidence, not only imagination. For this first half of the journey, we stay with what the evidence strongly tells us. The universe is expanding. The expansion is seen in the redshift distance relation of galaxies. The early universe was hotter and denser. The cosmic microwave background is the cooled remnant of ancient light released when the universe became transparent. The observable universe is limited by time, light, and expansion, not by a known physical wall. The whole universe may be much larger than the observable part, and may even be infinite. Expansion does not require a center. Expansion does not require an outside space in the standard description. Those statements already change the picture completely. The universe is not a bomb. It is not a ball flying into darkness. It is not a sphere with Earth at the center. It is not a growing cloud in a cosmic warehouse. It is a dynamic spacetime whose large-scale distances change with time. That may sound less visual than an explosion, but it is far more profound. An explosion uses space. Cosmic expansion changes space. An explosion has a center. Cosmic expansion can look similar from every location. An explosion moves into an environment. Cosmic expansion may include the environment itself. An explosion fades into the world around it. Cosmic expansion defines the world in which fading, distance, and arrival happen. This is why the phrase expanding universe is both true and incomplete. It names the observation, but it does not automatically teach the correct picture. To understand the phrase, we have to remove almost every everyday image attached to expansion. There may be no outside dark ocean. There may be no final shell of galaxies. There may be no border where space is being poured into nothing. There may only be more universe beyond our horizon, and beyond that, more again, or a topology so strange that our words break down. But then another question appears. If the universe is not expanding into empty space, why is there anything like space at all? Why does the universe have a geometry that can change? Why does it have laws that allow expansion, cooling, structure, stars, and life? Why is there a scale factor, a speed of light, a gravitational law, and a cosmic history instead of nothing? These questions reach beyond expansion into the foundations of existence. Science can approach some of them. Philosophy and mathematics surround others. But the expansion of the universe is one of the rare places where the deepest questions leave measurable fingerprints. A stretched wavelength, a microwave afterglow, a pattern of galaxies, a dim supernova farther away than expected, a cosmic web shaped by gravity and time. On human timescales, the sky seems almost eternal. The stars rise and set. The Milky Way returns in dark places. The constellations feel ancient and fixed. But this stillness is an illusion created by our short lives. On cosmic timescales, everything changes. Stars are born and die. Galaxies merge, black holes grow. Clusters form, voids widen. Light stretches, horizons shift, the universe cools, and the space between the largest structures keeps changing. This is the quiet terror of cosmic expansion. It is not loud, it does not announce itself in the night sky. It does not shake the ground. It does not pull the moon away by some dramatic force. It works almost invisibly across distances so vast that a human lifetime cannot watch them change directly. Yet, it controls the entire fate of the cosmos. If expansion had been slightly different in the early universe, structure might not have formed in the same way. Too fast, and matter could have dispersed before gravity built galaxies. Too slow, and the universe might have recollapsed before stars and planets had time to develop. The cosmos we see exists in the balance of expansion, gravity, radiation, matter, and dark energy. We live inside the outcome of that balance. Every galaxy is a fossil of it. Every atom heavier than hydrogen is a later chapter made possible by stars, which were made possible by gravitational collapse, which unfolded inside an expanding universe. Even the darkness between stars is part of the story. The night sky is dark partly because the universe has a finite age, because light from all regions has not had infinite time to reach us, and because expansion stretches and dims distant light. The darkness is not empty meaninglessness. It is evidence. But what is it expanding into? Maybe the most honest first answer is this. The universe is not expanding into a place the way smoke expands into air. The universe is expanding because the distances within it are increasing. If there is something beyond the whole universe, our current observations do not require it, and our standard language may not describe it. The outside, we imagine, may be a shadow cast by human intuition, not a feature demanded by the cosmos. But there is a second answer, more open and more mysterious. We do not know whether our observable universe is all that exists. We do not know the complete global shape of space. We do not know the true nature of dark energy. We do not know whether the hot Big Bang was an absolute beginning or part of a deeper process. We do not know whether a future theory will reveal a larger reality in which our universe is only one region, one bubble, one phase, or one solution among many. So the question is not dead. It has simply changed. Instead of asking where the universe is expanding inside ordinary space, we ask what space itself is. We ask whether space is fundamental or emergent. We ask whether the geometry of the universe is finite, infinite, curved, flat, simple, or connected in ways we cannot observe. We ask why dark energy exists, and whether it will keep accelerating the expansion forever. The simple question becomes a doorway, and behind that doorway is not a bigger room that we can easily draw. It is a deeper mystery about reality itself. For now, picture the universe not as a ball rushing outward, but as a vast cosmic web whose largest distances slowly scale upward with time. Galaxies gather where gravity wins. Voids open where matter is sparse. Ancient light stretches as it crosses the changing geometry. Horizons form not from walls, but from the finite speed of signals and the age and expansion of the cosmos. You are not near the center. You are not near an edge. You are inside a universe where every sufficiently distant place is part of the same expansion. Above you, the night sky looks like a dome of stars. Beyond those stars is the Milky Way. Beyond the Milky Way are other galaxies. Beyond the galaxies we can see are regions whose light has not reached us. And perhaps beyond those regions, if the universe continues, there is not outside darkness, but more of the same cosmic story, forever beyond our horizon. This is the first major step toward understanding the question. The universe expands, but not the way an object expands. The Big Bang happened everywhere, not at a point in space. The observable universe has a horizon, not a known wall. Expansion stretches light, changes distances, cools radiation, and shapes cosmic history. But none of this yet tells us the final fate of the universe. Because the expansion is not merely continuing, it appears to be accelerating. And that changes everything. If dark energy remains constant, the distant universe may fade beyond reach. If dark energy changes, the future could be stranger. If our understanding is incomplete, the expansion may be a clue to physics beyond anything we currently know. The question, what is the universe expanding into, may not have the simple outside answer our minds want. But it leads directly to an even more haunting question. If space itself can grow, accelerate, hide galaxies beyond horizons and perhaps continue forever, then what is the universe ultimately becoming? That is where the second half of this journey begins. Not at a wall, not at a glowing border, not at the place where galaxies run out and some larger darkness begins. It begins with the future. Because once you understand that the universe is not expanding into ordinary empty space, the question changes shape. It is no longer only about what might be outside. It becomes a question about what expansion is doing, what controls it, and what kind of reality it may leave behind. For most of cosmic history, gravity seemed like the obvious ruler. Matter attracts matter. Galaxies pull on galaxies. Clusters pull on clusters. If the universe began in an incredibly hot, dense state and then started expanding, it would make sense to imagine that gravity should slowly fight that expansion. Not necessarily stop it, but slow it down. That was the expectation for a long time. A universe full of matter should not race apart more and more quickly. It should expand while gravity tugs on every region, like a thrown stone climbing into the sky. The stone may keep going if it has enough speed, or it may fall back if gravity wins. But either way, the pull is backward. Then, astronomers looked deeper. They used exploding stars as distance markers. Type 1a supernovae are not perfect cosmic light bulbs, but they are regular enough that, with care, they can reveal how far away their host galaxies are. When scientists compared those distances with redshift, they found something that did not fit the simpler story. The expansion was not merely continuing, it was accelerating. Distant galaxies were not just being carried away by the growth of space. The pattern suggested that the growth of space had changed over time. In the early universe, matter and radiation shaped the story strongly. Gravity did slow the expansion. But billions of years later, another influence became dominant. We call it dark energy. That name sounds like an explanation, but it is mostly a label for ignorance. It does not mean astronomers found a glowing substance hidden between galaxies. It does not mean there is a dark wind pushing the cosmos outward from the outside. It means observations point to something in the universe that behaves as if it has negative pressure, something that makes the expansion of space accelerate on the largest scales. The word energy is familiar. The thing itself is not. Dark energy may be the energy of empty space, a cosmological constant built into the geometry of the universe. Or it may be something more dynamic, a field that changes slowly with time. Or it may be a sign that our theory of gravity, so successful across so many scales, still hides a deeper layer when applied to the entire cosmos. This is why the second half of the question is so haunting. If space can expand, and if that expansion can accelerate, then the universe is not simply becoming larger in a passive way. It is becoming more separated. Distances that are already huge are being stretched into distances that can become unreachable even in principle. Galaxies that we can observe today may one day slip beyond a horizon, not because they cross a physical wall, but because the space between us and them grows too quickly for any future signal to overcome. This is not ordinary motion. A galaxy far away is not necessarily traveling through its local space faster than light. Locally, physics remains normal. Light still moves at light speed through nearby space. A spaceship still cannot simply accelerate past the speed limit set by relativity. But when the distance between extremely remote regions increases, because the geometry itself changes, the total separation can grow faster than light without breaking the local rules. That idea feels almost unfair. We are used to speed meaning motion through something. But cosmic expansion is measured in a different way. The farther a galaxy is, the more space there is between here and there, and the more stretching can occur along the path. So the most distant galaxies can recede from us faster than light, not because they are violating relativity, but because the universe is not using the same category our intuition wants to use. This is where horizons become important. A horizon is not always an object. On Earth, the horizon is a line created by curvature and distance. There is no painted circle on the ocean where the world ends. Sail toward it and it moves. It is real as an observational limit, but not real as a wall. Cosmology has horizons too. The observable universe is defined by the light that has had time to reach us since the universe became transparent. Beyond that region may be more universe, but its light has not arrived. That boundary is not an edge of existence. It is an edge of our view. But there is another kind of horizon that belongs to the future. If expansion continues to accelerate, there are regions whose light can reach us now, but whose future light never will. A galaxy may be visible in our telescopes today because photons left it long ago, when the universe was smaller and the path between us was less stretched. Yet if that galaxy emits a new flash of light far in the future, that new flash may never reach the Milky Way. The galaxy will not vanish instantly. It will fade by stages. Its light will be stretched to longer and longer wavelengths. Its clocks, as seen from here, will appear slower and slower. Its image will grow dimmer, redder, colder, as if the universe is lowering a curtain made not of matter, but of distance itself. This is one of the strangest consequences of accelerated expansion. The universe does not need an outside to become unreachable. It can hide parts of itself from other parts by expanding. Imagine two distant civilizations in galaxies far beyond one another. In the young universe, signals might have crossed between the regions. In the future, if dark energy keeps driving accelerated expansion, their descendants may occupy cosmic islands separated by a growing ocean of space. Each island may still contain stars, planets, histories, and minds, but the others will drift out of contact forever. Not behind a wall, beyond a horizon. This is why the phrase, expanding into what, can distract us from what expansion actually does. The deeper drama is not that galaxies are pushing into an external void. The deeper drama is that the relationships between galaxies are changing. The universe can make two places less and less connected without sending either one through a boundary. It does this by changing the scale of distance. Cosmologists often talk about the scale factor of the universe. This is a way of describing how the distances between distant, unbound regions change with time. If the scale factor doubles, then two galaxies that are not gravitationally bound and were once separated by one amount of cosmic distance are now separated by twice that amount. This does not mean every object doubles in size. Earth does not expand with the universe. Your body does not expand with the universe. The solar system does not slowly swell because space is stretching inside it. Gravity, electromagnetism, and other local forces hold bound systems together. The expansion of the universe becomes significant only on enormous scales where galaxies are not tied tightly enough to resist the overall growth of space between them. This distinction matters because without it, cosmic expansion sounds absurd. If space is expanding everywhere, why does a ruler not expand? Why does the distance from Earth to the Moon not simply grow? Because space itself is stretching. Why do atoms remain atoms? The answer is that expansion is not a magic force tearing every distance apart equally at all scales. It is a large-scale behavior of the universe described by general relativity. In bound systems, local forces dominate. Atoms are held by electromagnetism. Planets are held by gravity. Galaxies and clusters can be held together by their own gravity. The universe expands between the structures that are not bound strongly enough to remain together. So the future of expansion is not a smooth separation of every possible thing from every other thing. It is more selective. Our local group of galaxies, including the Milky Way and Andromeda, is gravitationally bound. Andromeda is not being carried away from us by cosmic expansion. It is moving toward us. In the distant future, the Milky Way and Andromeda are expected to merge into a larger galaxy. For observers living in that far future, the local sky may contain the combined remains of both systems. But beyond the local group, the wider cosmic web will recede. The great clusters and superclusters that fill today's deep maps will become harder to see. Their light will stretch. Their signals will weaken. The evidence that there was once a vast network of galaxies may become buried under the limits imposed by expansion. Imagine astronomers born trillions of years from now around a long-lived star. They may look into the sky and see their own merged galaxy. They may see ancient stars, stellar remnants, perhaps faint gas clouds, and the last slow fires of cosmic history. But the distant galaxies that told us the universe is expanding may be gone from view. Not destroyed, not erased from existence, simply carried beyond the reachable universe. Those future astronomers might not easily discover the Big Bang. They might not see the same cosmic web. The cosmic microwave background, already faint, would be stretched to wavelengths so long and temperatures so low that detecting it could become nearly impossible. The evidence written across our present sky may fade with time. That is a chilling thought. We live in an era when the universe is old enough to contain stars, planets, heavy elements, and observers, but young enough that the early universe is still visible. We can still see distant galaxies. We can still measure redshift. We can still detect the afterglow of the hot early cosmos. We arrived during a window when the universe can tell its own story. The sky is not just beautiful, it is timed, and this timing gives the expansion question an emotional weight. The universe is not merely getting bigger, it is slowly changing what can be known. To ask what it expands into is to ask for a border. But the universe may be giving us a different answer. It expands into a future in which horizons grow more important than edges. Still, the human mind returns to the same image. If everything is expanding, surely there must be a boundary somewhere. Surely if we could travel far enough in one direction, we would reach the end. Surely beyond the last galaxy, there must be a region that is not universe. This is where geometry becomes stranger than imagination. A universe can be finite without having an edge. That sentence is easy to say and difficult to believe. The classic analogy is the surface of Earth. A creature living only on the surface could travel in any direction and never find an edge. The surface has a finite area, but no border where the surface suddenly stops. Keep going straight long enough and you can return to where you began. This does not mean the universe is literally the surface of a sphere. The surface analogy is two-dimensional. Our universe has 3 dimensions of space, at least in ordinary experience. But the analogy helps loosen the mind. It shows that finite does not automatically mean edged. A space can be complete, curved, and borderless. If the entire universe were shaped in an analogous higher dimensional way, then asking what lies beyond its edge would be like asking what lies north of the North Pole. The question uses a direction that stops making sense. You can stand at the North Pole. You can move away from it. But you cannot go farther north because north is defined by paths on the surface, and that coordinate has reached its limit. The problem is not that there is a hidden wall. The problem is that the language has been stretched beyond its proper use. In a similar way, asking what the universe expands into may be asking for a location that is not part of the geometry described by the universe itself. This does not prove that there is no larger reality. It only shows that expansion does not require one in the simple way our intuition assumes. There may be a bigger mathematical framework. There may be dimensions or structures beyond what we observe. There may be other regions born from inflation, other cosmic domains with different histories. But none of those possibilities is required just to explain ordinary cosmic expansion. The expansion we measure can be described from inside the universe. No outside room is necessary. That does not mean the idea of outside is meaningless in every possible theory. It means the word outside must be handled carefully. Outside of the observable universe is not the same as outside of the whole universe. Outside of our horizon may simply mean more space, more galaxies, more regions whose light has not reached us. Outside of the entire universe, if such a phrase applies at all, is a deeper, and far more speculative idea. This distinction is often where confusion begins. The observable universe is a sphere around us, roughly defined by how far light has been able to travel through cosmic history. But it is not a sphere floating in darkness. It is the part of the universe available to our view. An observer in a distant galaxy would have their own observable universe, centered on them, overlapping with ours in some regions and extending beyond ours in others. Every observer has a horizon. No observer has been shown to sit at the center of everything. This is why diagrams can be dangerous. A diagram must place the universe on a page. It must draw a circle, a sphere, a timeline, or a cone. It must put the cosmic microwave background on a shell. It must represent the Big Bang as a surface, or a point, or a bright beginning at one side of the image. These drawings are useful, but they smuggle in an outside view. They make us feel like we are looking at the universe from beyond it. But in reality, there may be no such viewpoint. We are inside the thing being described. Every telescope, every detector, every equation, every map of galaxies is built from information that reaches us within the universe. We never step outside, turn around, and photograph the whole cosmic object from a distance. Cosmology is the science of learning the shape of the forest while standing inside one of its trees. And yet, from inside, we have learned an astonishing amount. We know the universe was once hotter and denser. We know light from the early universe has cooled into the cosmic microwave background. We know galaxies are distributed in a vast web of clusters, filaments, and voids. We know distant light is stretched by expansion. We know the expansion rate has changed across cosmic time. We know dark energy, whatever it truly is, appears to dominate the current large-scale behavior of the cosmos. And still, when we ask whether the whole universe is finite or infinite, the answer remains uncertain. The observable universe is finite. The entire universe may be infinite. If it is infinite, then expansion does not mean it grows from finite size into a larger finite size. Infinity does not become larger in the everyday sense. Instead, distances between far apart points increase, the density changes, the scale changes, but the universe can already be without edge and without total boundary. An infinite universe can expand without needing an outside, because it is not swelling like a balloon into a room. It is more like an infinite grid, whose spacing increases. The grid was already endless. The distance between neighboring marks simply grows. That image is not perfect, but it helps. An infinite hotel, with every room slowly becoming farther from the next room, does not require a wall moving outward. The hotel never had an outer wall. Expansion changes the distances inside the system, not the position of an exterior surface. If the universe is finite and unbounded, the story is different in shape, but similar in lesson. There may still be no edge. The total volume can grow without expanding into a surrounding emptiness in the ordinary sense. The geometry itself changes. Either way, the simple picture of a cosmic ball pushing into black space is not the picture modern cosmology gives us. The real picture is harder, but more powerful. Space is not merely a backdrop. Space is part of the physical story. In general relativity, gravity is not just a force pulling objects through a fixed stage. Matter and energy influence the geometry of space-time, and that geometry influences how matter and light move. The universe, on the largest scales, is described by a changing geometry. Expansion is not something happening inside space-time, in the same way a firework expands inside the sky. Expansion is part of what space-time is doing. This is why there is no center of expansion in the usual sense. When a raisin bread dough rises, every raisin sees the other raisins moving away. No raisin has to be at the central point of the expansion within the dough. The space between raisins increases as the dough stretches. The analogy fails if pushed too far, because bread expands into a kitchen, while the universe does not need a kitchen. But for the inside view, it shows why every distant galaxy can appear to recede without placing us at the center. Everywhere can be a place from which the rest appears to expand. That is not because every place is secretly central. It is because the expansion is a change in the distance scale itself. If you could teleport to a galaxy billions of light years away and look out from there, you would see distant galaxies receding too. You would not find yourself at the edge. You would not see the Milky Way near some special middle. You would be inside the same large-scale pattern. This is one of the most humbling discoveries in science. The universe does not arrange itself around us. It only appears centered on us, because observation always begins where the observer is. Your horizon surrounds you because light reaches you from all directions. A distant observer has a different horizon. A future observer will have another. None of these horizons is the wall of reality. They are the limits of information. And the limits of information are not always the limits of existence. The question then becomes sharper. If the universe may have no edge, and expansion may not require an outside, why does the question feel so unavoidable? Because the human brain evolved in a world of objects. Everything around us has a boundary. A stone has a surface. A house has walls. A cloud has a vague edge. A country has borders. Even the ocean, which feels endless from ashore, is wrapped around a planet. When something expands, it occupies more of its surroundings. Our intuition is built from containers. But the universe is not obviously a container inside a larger container. It may be the total arena in which container and contained are defined. That is why this subject feels almost like a language problem. We take words shaped by ordinary life, such as space, outside, before, edge, center, and expansion, then apply them to the totality of reality. Sometimes they work. Sometimes they bend. Sometimes they break. The Big Bang gives another example. People ask what happened before the Big Bang, as if the Big Bang were an explosion at a time inside a larger time. But in many cosmological models, time itself as we know it is part of the universe's history. Asking what happened before may be like asking what is north of the North Pole. It may point toward a real mystery, but the ordinary grammar of the question may not survive. The same is true of outside. Outside may be a real mystery, but it may not be a place. It may be a sign that our imagination has reached the edge of its old categories. Still, scientists do not simply shrug and stop. They replace vague pictures with measurable questions. Curvature is one of the most important clues. A flat universe in cosmology does not mean a thin sheet. It means that on large scales, geometry behaves in a way similar to ordinary Euclidean space. Parallel lines remain parallel. The angles of very large triangles add in the familiar way. A positively curved universe would be different, somewhat analogous to the surface of a sphere, but in 3 dimensions. A negatively curved universe would have another kind of geometry. Measurements of the cosmic microwave background suggest that the observable universe is very close to flat. But close to flat does not automatically mean infinite. A small patch on Earth looks flat if you cannot see enough of the planet. In the same way, the observable universe might be a patch of a much larger curved whole. If the total universe is far bigger than the part we can see, its curvature could be too subtle for us to measure clearly. This is another way the cosmos resists simple answers. Our measurements can tell us much about the observable region. They may not fully reveal the global shape beyond the horizon. The universe could be infinite and flat. It could be finite with a curvature so gentle that our visible region looks almost flat. It could have a more complex topology, where space connects to itself in ways that are difficult to picture. And that brings us back to the balloon analogy. You have probably heard that the expanding universe is like dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. There is no center on the surface. The surface itself expands. This analogy is useful, but it is also dangerous. The balloon expands into the room around it. The surface is embedded in a larger space that we can see. So people naturally ask, what is the cosmic room? What is the air outside the universal balloon? But in the analogy, the creatures on the balloon surface are not supposed to use the room. Their universe is the surface. The outside direction is not part of their space. It is only there because we, as higher dimensional observers, need a way to picture the curvature. The real universe may not need to be embedded in a higher dimensional room to expand. Mathematics can describe the intrinsic geometry of a space without requiring an external viewpoint. Intrinsic means measured from within. A creature living on a surface can measure distances, angles, and curvature without stepping into the outside dimension. In the same way, cosmology describes expansion using relationships between distances, light, time, and geometry inside the universe. The outside is not part of the measurement. This is why the most careful answer to the title question is not a dramatic image, but a correction. The universe is not expanding into anything that we know of. The distances within the universe are increasing. That answer can feel disappointing because it removes the picture instead of replacing it with a larger one. But the removal is the point. The old picture was misleading. A child asks, where does the road go after the end of the map? Sometimes the answer is, the map is incomplete. Sometimes the answer is, the road continues beyond the map. But sometimes the answer is, the map was never a picture from outside. It was a coordinate system made by someone standing on the road. The cosmic map works more like the third case. When we draw the observable universe as a sphere, we are not drawing the whole universe from outside. We are drawing the region from which light has reached one observer. The edge of that sphere is not a cliff. It is the oldest light we can receive. Beyond it may be more universe. And if inflation is correct, there may be vastly more. Inflation is the idea that in an extremely early fraction of cosmic history, the universe expanded at an extraordinary rate. It was proposed to solve several puzzles, including why the universe looks so uniform in temperature across regions that otherwise seem too far apart to have exchanged information, and why space appears so close to flat. Inflation, if it happened, could mean that the universe beyond our observable horizon is enormous compared with the part we see, possibly so enormous that our observable universe is like a tiny patch inside a much larger whole. In some versions of inflation, the process does not end everywhere at once. Different regions may stop inflating and become pocket universes, while inflation continues elsewhere. This leads to the idea of an eternal inflation multiverse. But we have to be careful. This is not the same as saying the universe is expanding into a visible black void. It is not something we have directly observed. It is a possible consequence of certain models, not a simple answer written across the sky. If such a larger inflationary structure exists, then what we call our universe may be one region inside a broader reality. But even then, the expansion we observe inside our region is still not the motion of galaxies into an ordinary outside space. It is the stretching of space-time within our cosmic domain. The multiverse, if real, does not rescue the balloon picture in a simple way. It makes the question deeper, not easier, because then we would ask what the larger structure is. What is its geometry? Does it have time like ours? Does it have a beginning? Are there laws beyond our laws? Does the word outside apply there? Or does it fail again at a higher level? Every time we try to put the universe inside something else, the same question follows the container upward. What is that container inside? And what is that inside? At some point, either reality has a final structure that is not inside anything, or our language of inside and outside stops applying. Cosmology pushes us toward that limit. This does not mean the mystery is fake. It means the mystery is larger than the image that first created it. The ordinary question imagines a universe with an edge moving into empty space. The real question asks why there is a geometry at all, why it evolves, why it has the laws it has, and why those laws allow distance, time, matter, radiation, and observers to emerge. That is much stranger than an expanding bubble. Now let us return to dark energy, because it may decide how lonely the future becomes. If dark energy is a cosmological constant, then its density does not dilute as the universe expands. Matter becomes thinner. Radiation cools and stretches. But the energy associated with empty space remains constant per unit volume. As the universe grows, the total amount of this dark energy-like influence grows with the volume of space. That sounds almost impossible. In ordinary life, if you expand a gas, its density drops. If you spread particles through a larger volume, they become thinner. But a cosmological constant behaves differently. Empty space itself carries the same energy density, so more space means more of that energy in total. This is one reason dark energy is so mysterious. It seems connected not to objects inside space, but to the nature of space itself. If that remains true forever, the universe moves toward a future often called heat death, or the big freeze. The phrase does not mean everything freezes like water in a freezer. It means the universe becomes colder, darker, more dilute, and less able to support processes that require usable energy differences. Stars will not shine forever. Galaxies will use up their gas. New star formation will slow. The brightest era of the universe will pass. Long after familiar stars die, smaller red dwarfs may continue to burn for immense stretches of time. Then they too will fade. White dwarfs will cool. Neutron stars and black holes will remain. Over even longer timescales, if protons decay, matter itself may slowly fall apart. If black holes evaporate through Hawking radiation, even they may eventually disappear into a thin bath of particles and radiation. These timescales are so enormous that they almost stop feeling like time. 1 trillion years is already far beyond human history. A quadrillion years is beyond the lifetime of ordinary stars. The evaporation time of the largest black holes is written with numbers so large that they feel less like dates and more like monuments to our ignorance. But the direction is clear in the standard picture. The universe becomes emptier. Not empty in the sense of reaching an outside void. Empty in the sense that its own contents become more thinly spread, more isolated, and less able to interact. This is one possible answer to what the universe expands into. It expands into loneliness, not as poetry, but as physics. Regions that once shared light become causally disconnected. Galaxies outside our gravitationally bound neighborhood fade beyond horizons. The cosmic microwave background cools toward undetectability. The universe does not need to die in a fiery collapse. It may fade by making communication impossible. But this future depends on dark energy staying the way it appears today. And dark energy may not be simple. One possibility is quintessence, a dynamic form of dark energy that changes with time. In that case, the acceleration might strengthen, weaken, or even end. The universe's future could be different from the cosmological constant picture. If dark energy weakens enough, expansion might continue but slow. If it changes sign in some models, the universe might eventually stop expanding and begin to contract. If it grows stronger with time, in a phantom energy scenario, the future could become more violent. The most extreme version is called the Big Rip. In a Big Rip universe, dark energy becomes so dominant that expansion does not merely separate galaxy clusters. It eventually overwhelms smaller and smaller bound systems. First clusters separate, then galaxies, then solar systems, then planets, then molecules. In the final moments, Even atoms would be torn apart by the accelerating expansion. This is not the favored standard picture, but it shows how much depends on the true nature of dark energy. The same observation, accelerated expansion, opens several doors. One door leads to slow fading, another leads to future change, another leads to collapse, another leads to a cosmic tearing apart. To know which door is real, we need to know whether dark energy is truly constant. That is one reason modern cosmology is entering such an important era. Telescopes and surveys are not only making prettier maps, they are measuring the expansion history of the universe with increasing precision. They are mapping galaxies across billions of years of cosmic time. They are studying supernovae, gravitational lensing, galaxy clustering, and the large-scale structure of matter. The aim is not just to ask how fast the universe expands today. It is to reconstruct how expansion changed. A single measurement is like hearing one note from a song. The history of expansion is the melody. Dark energy may be hidden in the way that melody bends. If the notes match a cosmological constant, then the standard model becomes stronger. If they drift, something deeper may be happening. That deeper thing could be a new field. It could be modified gravity. It could be a subtle error in how we measure cosmic distances. It could be a clue that our best model is only an approximation to a more complete theory. Science advances by refusing to protect its most successful ideas from better evidence. The current model, often called lambda CDM, is remarkably powerful. Lambda represents the cosmological constant, and CDM stands for cold dark matter. Together with ordinary matter, radiation, and the geometry of space-time, this model explains a vast amount. The cosmic microwave background, the distribution of galaxies, the abundance of light elements, the growth of structure, and the accelerated expansion. But it is not a final explanation. It contains dark matter, whose particle nature remains unknown. It contains dark energy, whose physical origin remains unknown. It contains an early universe whose deepest beginning remains beyond tested physics. It works astonishingly well, and yet it tells us that most of the cosmic inventory is still mysterious. That is not failure. That is a map with blank regions clearly marked. And one of those blank regions sits at the heart of the title question. If space itself can have energy, if empty space can shape the future, then nothing is not as simple as we thought. The emptiness between galaxies is not just absence, it has geometry. It can stretch light, it can carry fields, it can have quantum properties, it may even determine the fate of everything. So when someone imagines the universe expanding into empty space, they may be using the wrong kind of emptiness. The emptiness inside the universe is already a physical thing. The hypothetical emptiness outside the universe is not something we have measured. It may not be meaningful. It may not be needed. It may be a placeholder, created by our minds because we cannot imagine totality without a surrounding background. This is why the answer cannot be reduced to one sentence without losing the wonder. The universe is expanding into nothing. The universe is expanding into itself. The universe is not expanding into anything. Each phrase can be useful, but each can also mislead. Into nothing may make people imagine a black void outside. Into itself may sound mystical. Not into anything may sound like avoidance. A more careful answer is this. The expansion of the universe is the increase of distances within space-time on the largest scales. It does not require an external space into which the universe moves. The observable edge is a horizon, not a boundary. The whole universe may be infinite, or finite and unbounded, and current observations do not give us a simple outside wall. That answer is less cinematic than a glowing cosmic bubble. But it is far more astonishing, because it means the universe is not an object in space. Space is one of the things the universe is. And if space changes, The question cannot be answered using the same mental picture we use for smoke, balloons, or explosions. Now consider the word into again. It implies a destination. A seed grows into a tree. A child grows into an adult. A cloud expands into the sky. So perhaps instead of asking what space expands into as a location, we can ask what the universe is expanding into as a state. What is it becoming? In the present era, it is becoming more dominated by dark energy. It is becoming more divided by horizons. It is becoming colder on average. It is becoming less dense. Its large-scale structures are becoming more isolated. The galaxies that are already gravitationally bound will continue their local stories, but the grand cosmic web will become less accessible to any one observer. The universe expands into a future where the whole becomes harder to see from any part. That may be the most honest, poetic answer. Not an outside place, a different condition. A cosmos whose past was hot, dense, bright, and connected, and whose far future may be cold, sparse, dim, and separated. Yet even that future is not the final word, because our knowledge is not complete. At the deepest level, expansion points to the unfinished union of gravity and quantum physics. General relativity describes space-time as geometry. Quantum theory describes fields and particles with probabilities, fluctuations, and uncertainty. Both frameworks are extraordinarily successful in their own domains. But the earliest universe, the nature of the Big Bang, and perhaps the true origin of dark energy, ask for a theory that can handle both together. Without such a theory, the phrase "the beginning of the universe" remains partly hidden. If we run the equations of general relativity backward, the universe becomes hotter and denser, and eventually we reach conditions where the equations point toward a singularity. But a singularity is often not a physical object. It is a sign that the theory has been pushed beyond where it can safely answer. The Big Bang, in modern cosmology, is not simply a tiny dot that exploded. It is the limit of our tested description of the early hot universe. What happened at the very earliest moment, or whether there was a before, in some deeper sense, remains unknown. Some models imagine a bounce from a previous contracting phase. Some imagine inflation emerging from quantum conditions. Some imagine time itself becoming different near the beginning. Some suggest that the question of before may not be well defined. These are not settled facts. They are attempts to reach beyond the horizon of current knowledge. And they matter because the question expanding into what may be connected to a deeper question. What is space-time made of? If space-time is fundamental, then expansion may be a basic behavior of the universe as a whole. If space-time emerges from something deeper, then expansion may be the large-scale appearance of underlying degrees of freedom we do not yet understand. In that case, the universe might not be expanding into a place. It might be evolving within a deeper structure, where our familiar idea of place is only approximate. This is difficult, but not impossible to approach. Think of temperature. Temperature feels like a basic property. A room is warm or cold. A star is hot. Space is cold. But temperature is not fundamental in the same way for a single particle. It emerges from the motion and distribution of many particles. Maybe space-time is somewhat like that. Maybe distance, geometry, and expansion are large-scale concepts that emerge from something more basic. We do not know. But if that turns out to be true, then the question of what the universe expands into might be like asking what a temperature expands into. It would be using a macroscopic concept outside the domain where it makes sense. That possibility does not make the universe less real. Temperature is real. Sound is real. Waves are real. But they are real as patterns, not as the deepest ingredients. Space-time may be similar, though this remains one of the greatest open mysteries in physics. This is why cosmology can feel both precise and dreamlike. We can measure the temperature of the cosmic microwave background with incredible accuracy. We can map millions of galaxies. We can calculate how light bends around massive clusters. We can estimate the age of the universe. We can simulate the growth of structure from tiny early fluctuations. And then, after all that precision, we still face questions that sound almost childlike. Where is the universe? What is it inside? Why is there space? Why does time move the way it does? What is the future of everything? The simplicity of the questions is not a weakness. It is a sign that they sit beneath the technical language. A good scientific answer does not kill the wonder. It sharpens it. The universe is expanding not because galaxies are fleeing a central explosion, but because space-time on the largest scales is evolving. It is not expanding into an observed external emptiness, because the expansion is not the motion of a boundary through a container. The observable edge is not the edge of the universe, but the limit of ancient light. The whole universe may be infinite, or it may be finite without an edge. Dark energy is causing the expansion to accelerate, though its true nature remains unknown. And if the current picture continues, the far future becomes a place of horizons, fading light, and cosmic isolation. That is already enough to change how we look at the night sky. When you look up, you are not seeing a static dome. You are seeing an ancient record of distances that are changing. The stars in our galaxy belong to a bound island. The galaxies beyond belong to a larger pattern that is slowly being stretched. Some of the light entering your eyes began its journey before Earth had complex life, before the sun formed, before the Milky Way looked the way it does now. Every photon is a survivor of expansion. Its wavelength carries history. Its arrival proves that some connection still remains between here and there, but not all connections last forever. In a universe with accelerated expansion, the night sky is not only a window, it is a closing window. Not for us in any human lifetime, not for civilizations on ordinary timescales, but on cosmic timescales, the view changes. The most distant galaxies become unreachable. The early afterglow fades. The evidence of the wider universe becomes harder to recover. The present cosmic age is therefore special, not because we are important, but because information is still available. We can see far enough to know we are not alone in the cosmic web. We can see early enough to know the universe had a hot beginning. We can see precisely enough to know expansion is accelerating. We can still ask the question while the universe leaves clues, and the clues point away from the simplest mental picture. There is no known outer darkness into which the universe pours. There is no known edge racing away from a center. There is no known outside wall waiting beyond the last galaxy. There is space, time, matter, radiation, dark matter, dark energy, geometry, and horizons. There is an observable universe, and there may be far more beyond it. There is expansion, and there is the strange fact that expansion can be real without being expansion into a surrounding place. This may be the hardest part to accept. The universe is not obligated to fit the categories that helped our ancestors survive on Earth. A mind trained by caves, rivers, fires, and skies tries to imagine the totality of existence. It reaches for boundaries because everything nearby has boundaries. It reaches for outside because every room has a door. It reaches for before because every event in life follows another event. Cosmology gently removes those handles, not to make the universe smaller, to reveal that it was never small enough for those handles in the first place. If the universe is infinite, then there may be no outer edge at all. If it is finite and unbounded, there may still be no edge. If it is part of a larger multiverse, then our observable region is not the whole story, but the expansion we measure still does not become a simple explosion into empty space. If space-time is emergent, then the word into may fail at an even deeper level. Every serious possibility is stranger than the common picture, and that is why the title question survives. It is not answered by saying, simply, nothing. It is answered by learning why the question was so tempting, where the temptation misleads us, and what deeper mysteries remain after the mistake is removed. In the end, the universe may not be expanding into something, it may be expanding as something, as a changing geometry, as an evolving space-time, as a cosmic history that began in heat and density, formed atoms and stars, built galaxies and planets, produced observers, and now moves toward a future shaped by a force we still do not understand. That future may be quiet, it may be cold, it may be longer than imagination can comfortably hold. But it is not empty of meaning, because for a brief era, beings made from the ashes of stars could look across billions of light years and notice the pattern. They could discover that the galaxies were not still. They could find the afterglow of the early universe. They could measure the acceleration. They could ask what space is doing. They could realize that the question into what was not foolish, but incomplete. It was the first doorway. Beyond it lies a deeper view. The universe is not a ball in a room. It is the room, the distances, the clocks, the light paths, the horizons, and perhaps the rules by which rooms can exist at all. When it expands, it does not need to push into a place beyond itself. It changes what distance means between the places inside it. And when that change accelerates, the future becomes a landscape of fading signals. The galaxies beyond our local island will not crash into a cosmic wall. They will simply become unreachable. Their light will stretch. Their images will dim. Their stories will leave our sky. The universe will not announce this with a final explosion. It will happen quietly, across timescales so vast that silence becomes the dominant event. This is perhaps more unsettling than an edge. An edge would be dramatic. It would give the mind something to picture, a boundary, a cliff, a final surface. But a horizon is subtler. It does not say reality stops. It says contact stops. And in physics, contact is everything. To know something, a signal must reach you. To influence something, a signal must cross the distance. To share a universe in the practical sense, regions must remain connected by causal paths. Accelerated expansion threatens that connection on the largest scales. It divides without cutting. It separates without a blade. It hides without a wall. This is why the expanding universe is not just a topic about size. It is a topic about relationship. A static universe would have been strange enough. An expanding universe is stranger. An accelerating universe is stranger still. It tells us that cosmic history has direction, and that the direction is not simply from small to large, but from connected to isolated, from hot to cold, from visible to hidden. At least, that is the direction suggested by the simplest reading of current evidence. Future discoveries may alter the story. Dark energy may evolve. The Hubble tension may point toward new physics or hidden systematics. Large surveys may reveal subtle departures from the standard model. Quantum gravity may change what we mean by beginning, space, and time. But any future theory will still have to explain what we already see: redshift, the microwave background, the abundance of elements, galaxy structure, gravitational lensing, and the accelerated expansion discovered through distant supernovae and supported by later evidence. The old image of a central explosion will not return. The universe is too large for that. And more importantly, it is too geometrical. A firework expands through air. The universe expands by changing the metric that tells distant regions how far apart they are. A firework has a center. The universe, on large scales, offers no observed central point. A firework has an outside observer. We observe the universe from within. A firework uses space. The universe includes space. That comparison is the simplest way to see why the title question is both natural and misleading. Natural, because every expanding thing we know expands into something. Misleading, because the universe is not one more thing inside the world. It is the world, at least the physical world we can describe. And maybe that is where the answer becomes quiet. The universe expands into no surrounding darkness that science has found. It expands by increasing the distances between unbound regions of space. It expands from everywhere, not from a center. It may be endless, or it may be finite without an edge. Its observable limit is a horizon created by light, time, and expansion. Its future depends on dark energy, one of the deepest unknowns in modern physics. And if the acceleration continues, the universe will become a place where more and more of reality lies forever beyond communication. For now, every galaxy we see is a message from a different time. Every redshift is a record of stretching. Every patch of the microwave background is a fossil of a hotter universe. Every measurement of acceleration is a reminder that the future is being shaped by something we have not yet named in any final way. And every night sky is a temporary gift, not because the stars above your head will vanish tomorrow, but because the cosmos is not frozen. It is changing. It has always been changing. From the first hot light to the first atoms, from the first stars to the first galaxies, from the first planets to the first minds that could ask questions, the universe has never been a still backdrop. It is a history, and expansion is one of the ways that history moves. So when you hear that the universe is expanding, do not picture a sphere swelling into darkness. Picture every unbound distance in the cosmic web slowly being rewritten. Picture ancient light stretched by the journey. Picture horizons forming where no walls exist. Picture galaxies fading not because they are destroyed, but because the road between here and there grows too quickly for future messages to cross. Picture space not as emptiness, but as the dynamic structure in which emptiness, matter, time, and light become meaningful. Then, the original question changes. The universe is expanding. But into what? Into a larger darkness? Maybe not. Into a hidden higher dimension? Not required by what we observe. Into nothing. Only if we use the word nothing carefully. Into itself, only if we mean that its own internal distances are growing. Into the future? Yes. In the only sense that all physical history moves toward what comes next. And what comes next may be a universe where the evidence of the grandest structures slowly disappears from view. That is why our moment matters. We live while the cosmic story is still readable. We live while the microwave afterglow still surrounds us. We live while distant galaxies still reveal the expansion. We live while the universe is old enough to ask about itself, through us, and young enough to answer. One day, perhaps, the sky will be quieter. One day, the far galaxies may be gone beyond the horizon. One day, the universe may appear smaller to those who remain, not because reality has shrunk, but because information has retreated. That future is not here yet. For now, the light still arrives. For now, the maps still grow. For now, the question still opens. The universe is expanding, and the answer to what it expands into is not a place you could point to. It is a lesson about space itself. Space is not a container waiting in the background. Space is active. Space has history. Space can stretch. Space can cool light. Space can build horizons. Space can make the visible universe a temporary island of knowledge inside a much larger unknown. And perhaps the most astonishing part is that we can say any of this at all. On a planet that formed long after the first stars, around a star that will one day die, inside a galaxy that will one day merge with another, in a universe whose distant lights are slowly slipping away, we have learned that expansion is not an edge moving outward. It is the changing geometry of everything we can measure. That may not satisfy the part of the mind that wants a wall, a beyond, a final outside, but it gives us something better, a universe that is not merely bigger than imagined, a universe that is different from imagination. And that is why this question remains one of the greatest doorways in all of science. Because when we ask what the universe expands into, we are really asking where reality ends. And the answer may be that reality does not end in the way our minds expect. It may end only in horizons. It may extend forever. It may curve back on itself. It may be one region of something larger. Or it may be that the word end belongs to objects inside the universe, not to the universe itself. The final answer is not yet known, but the false answer can be left behind. The universe expands. The light stretches, the horizons shift, the future opens. And the mystery remains, not because science has failed, but because science has carried us far enough to see how strange the question really is. This is the universe we inhabit. Not a sphere moving through darkness, not a blast from a central point, not a room filling another room. A changing space-time, filled with islands of matter, threaded by light, shaped by invisible components, and accelerating toward a future we are only beginning to understand. And if you let that image settle, the old question becomes quieter. The universe is expanding, but into what? Maybe into no thing, maybe into a future of its own geometry, maybe into a mystery that waits not beyond the stars, but beneath the meaning of space itself. And that may be far more terrifying and far more beautiful than an edge.